In this video, we are going to construct a discrete probability distribution table using the product rule for dependent events. So first, let's choose our scenario. Let's do a sampling without replacement scenario in which we have a shipment of 30 items. And let's say that in this shipment of 30 items, 5 items are defective. What we're going to do is randomly select 4 different items and test them to see if they are defective or not. And we will let our random variable x equal the number of defective items in the 4 selected. Now first I want to show that this is indeed a dependent experiment by showing that the number of the sample, in which case is 4, divided by the population size, in this case 30, is greater than 5%. We see it's 13%, so that is indeed greater than 5%, or 0.05. So this is indeed a dependent probability example, so we will be using the product rule for dependent events. So to construct our table, we need a column for x, the values of the random variable, and a column p of x for the associated probabilities. The values of the random variable, which represent the number of defectives in 4 items, range from 0 defectives up through 4 defectives. So 0, 1, 2, 3, 4 are the values of the random variable. And now we need to compute the probabilities. Well, the probability of 0 defectives is the same thing as the probability that all 4 items are good. So we want the probability of good, 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 good. We know that this is dependent, so we'll do the product rule for dependent events. So the probability that the first item is good, there are 25 good items since 5 items are defective, so the probability the first item is good is 25 out of 30. And the probability the second item is good is 24 out of 29 because we are sampling without replacement, and these are dependent events, so the probabilities are changing, so there are only 24 good items left, and since we had already taken a good item out, there's a total of 29 items left. So 2 good items are taken out, so now that the probability the third item is good is 23 out of 28. That item is also left out of the box, so the probability the fourth item is good is 22 out of 27 to give us 0.461595. Now we need to find the probability of exactly one defective. To find the probability of exactly one defective, we first need to find the number of ways to get one defective in the 4 selected items. We will then multiply that by the probability of one way to get a defective, let's say the first defective and the last 3 items good, because the probability of any one of those items being defective. So defective, good, 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 or good, defective, good, good, those all have the same probability. So to find the number of ways to get one defective in 4, we do a combination, which remember on Excel is a combin. So we're going to do combin of 4, choose 1. And then we'll multiply that by the probability of defective, good, good, good. Probability the first item is defective, 5 out of 30. Leave that item out. The probability the second one is good is 25 out of 29. Leave that item out. Probability the next one is good, 24 out of 28. Leave that item out. Probability last one is good, 23 out of 27. So we have 4 choose 1 times 5 out of 30, the probability the first one is good. There are only 29 items left in the box, but still 25 good ones, so the probability the second one is good is 25 out of 29, and then we decrease by 1 second one good, 24 out of 28, or I should say the third one good, 24 out of 28, and then the last one good, 23 out of 27, to get us 0.419631. Now to find the probability that exactly 2 are defective, we need to first compute the number of ways to get 2 defectives in 4 items. Then we'll multiply that by one of the way to have 2 defectives, and we'll just focus on the probability of defective, defective, good, good. So, starting off with the number of ways to get 2 defectives from 4 will be combin of 4 choose 2 times the probability the first one is defective, 5 out of 30, times the probability the second one is defective, 4 out of 29, times the probability the third one is good, 25 out of 28, times the probability that last one is good, 24 out of 27. And that gives us 0.109. Now let's do the probability of exactly 3 defectives. So we will start off with the number of ways to get 3 defectives in 4 items. Multiply that by one of the ways to get 3 defectives, and we will just focus on defective, 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 good. So the number of ways to get 3 defectives in 4 is combin 4 choose 3 times the probability the first one is defective, 5 out of 30, times the probability the second one is defective, 4 out of 29, times the probability the third one is defective, 3 out of 28, times the probability the last one is good, 25 out of 27, to get 0.009122. Now we will do the probability that all 4 are defective. That can only happen in one way, probability of defective, 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 defective. So to compute that, we start with the probability the first one is defective, 5 out of 30, times the probability the second one is defective, 4 out of 29, times the probability the third one is defective, 3 out of 28, times the probability the last one is defective, 2 out of 27, to get 0.000182. Let's go ahead and sum up these probabilities using an auto sum to make sure they add up to 1. And they do, so we know there have been no errors made. And here then is our finished probability distribution table. Now that we have our probability distribution table, let's go ahead and construct a probability histogram for it. So remember, we simply highlight the P of X column. I'm even going to highlight the label. I go to Insert, Column, 2D, and here's the initial probability histogram. We want to close these bars and add axis labels, so I go to the chart layouts, and chart layout 8 here does all those things. So now the gap's closed. I'm going to give it some contour so that we can distinguish the bars. So notice here we have a nice skewed histogram, a right skewed histogram. Horizontal axis has the wrong labels because those should be labeled with the x values of 0 to 4. So go to Select Data. We will edit the horizontal data, and we will highlight then 0 to 4 because that's what we want for our horizontal axis. Click OK. Click OK, and there's our horizontal axis. Let's now label the horizontal axis with X, vertical axis with P of X, and I will title this probability histogram. And there's our probability histogram. If we look at what the mean of this is, since the mean is a balance point, we can see the mean is going to be somewhere here between in the 0 and 1. So somewhere between 0 and 1 around here would probably be a good place to put our fulcrum to get it balanced. Let's actually find the mean of this probability distribution using the sum product. So remember, the mean is a weighted average of the values of the random variable weighted by the associated probabilities. So we go to Formulas, Math Trig, to find sum product. And our first array will be our random variables 0 through 4. And then we will have our weights p of x's as array 2, right? So your x's and then your p of x's, and we get 0.6 repeating. Because our random variables are to only one decimal place, they're just integers, we are going to round off our parameters, such as the mean here, to only one decimal place. So we'll call that 0.7. Next, let's compute the variance, a measure of spread or variation of the data. And this, remember, is a weighted average of the squared differences from the mean. So we are going to need another column here that represents x minus the mean squared, because we want the squared differences. I'm going to write a formula for this. So for x, I'm going to click on the first value for x, click on that cell, minus, I'm going to click on the mean. This way we'll be using actually the unrounded version of the mean in the computation of the squared difference. Close a parenthesis. Oh, we want to make sure that when we're writing a formula that the cell for the mean stays fixed, so that when I copy the formula it doesn't change the row designation. So I need to put $signs in front of the row and column designations. Quickest way to do that on a PC computer, though this does not work for a Mac, is to hit F4. So function F4 to get the $signs in front of both the column and row designations, and that will fix the cell so it won't change when I copy this formula. And then we will square that. So now I can copy this formula down. And I have a column of squared differences of the mean. So now I want to find a weighted average of the squared differences from the mean, where it's weighted with the probabilities. So we will do a sum product again. So we go into the math trig options to find sum product. Array 1 is my squared differences. Array 2, my weights, which are the probabilities. Okay, and we will round this to one decimal place. So that gives us 0.5. Now remember, this is a weighted average of squared differences. So this is in squared units. Squared units don't make sense to us. We want normal units. So to get our regular units back, the original units, we find the standard deviation. And the standard deviation is simply the square root of the variance. So SQRT will give us the square root. I will click on the variance because I don't want the rounded version. I want to square root the unrounded version. This gives us 0.7. Again, take that down to one decimal place, because what we want to do here is round our parameters to one more decimal place than the values of the random variable x. So we have then created a probability distribution table where the values of the random variable start at 0 and go up through the sample size. The associated probabilities were computed using the product rule for dependent events, where in the cases of 1, 2, and 3 defectives here, we had to use a combination to find out how many ways that could happen, and then multiply the number of ways it could happen by the probability of just one of those ways. And then that gave us a table to double check that all the computations are likely correct. Sum up the probabilities to make sure you have 1. That means we have a complete probability distribution table. Then we can find the parameters. A measure of central tendency, or a way of defining the middle, is the mean, which remember is a balance point here. That turned out to be 0.7, so around here, that's where you would put the fulcrum to balance this probability histogram. We found that using a sum product of the values of the random variable weighted by the probabilities. A measure of variation or spread of this data, we found computing the variances was a weighted average of the squared differences from the mean. So again, that was computed as a sum product where we took our squared differences and then weighted them by the probabilities. That value, though, is in squared units. So to get a nice measure of variation that is in regular units, the original units, we find the standard deviation, which is simply the square root of the variance. And we always want to round our parameters to one more value than one more decimal place than the values of the x or random variable.